First, I'll create some data to use when I do some interpolations. The function I'll use is y equals x squared plus 3 times e to the negative 3x. I'll evaluate the function at increments of 0.4 between x equals 0 and 2. Then calculate the corresponding values for y. And finally, I'll create an array of values where we want to interpolate the function. I'll interpolate the function over the range of 0 to 2 at increments of 0.01. The values where I'll interpolate the function will be in an array named xi. For later reference, I'll calculate the actual values of the function at these points and put them in an array named y_exact. Now let's see how interpolation works with the nearest, next, and previous options. First, I'll use nearest. The data points are the red circles and the interpolated values are the black line. The interpolation simply takes the value of the data point that it's closest to. I'll compare that to the next option. To compare the two approaches, first I'll hold the current figure. Then I'll use the next option to create the interpolated values. Now the interpolated points take on the value of the data point to their immediate right. Let's also use another very simple interpolation function, linear interpolation between adjacent points. Now the interpolated values just consist of connecting the dots with straight line segments. This is the approach that MATLAB uses in its plot function. So if I create a new figure and type plot x, y, I get the same figure as when I used linear interpolation. Before I do spline and cubic Hermitian interpolation, I'll clean things up by closing the current figure windows. I can do this with the close command. Now let's use spline and cubic Hermitian interpolation on this same set of data. In this case, the differences between the two interpolation approaches is subtle, so I'm going to plot the exact function values as well. MATLAB does complain a bit, since there's a new function called pchip that also performs cubic Hermitian interpolation, which will be replacing the cubic method. I'm used to using cubic, so I won't be switching over to the new function until the last minute. For this case, both methods look like pretty good approximations to the data, but it does look like the spline method is closer to the exact solution. The green dashed line is the exact solution, the black dotted line is the spline solution, and the solid blue line is the cubic Hermitian interpolation. Which interpolation approach is a best fit to the data depends on the data set. In the last example, the spline gave what seemed to be a better interpolation scheme than the cubic Hermitian approach. But let's take a look at a different data set. The data set I'm going to use is in these vectors. To visualize the data, I'll plot it. The data are at three discrete values, -1, 0, and +1. Now I'll set up a vector of interpolation points which are, of course, much more closely spaced than the data so that we can see the behavior of the interpolated function between points. Now let's compare the spline and cubic interpolations on this set of data. In this case, the cubic Hermitian approach seems to give a slightly better solution. The spline approach contains some oscillations that aren't really indicated by the data itself. Finally, let's do a linear fit to the data. I want to add this to the existing plot, so I'll hold this plot. Now I can add a linear interpolation to the plot with these commands. The linear interpolation, the green line, seems to be a good approximation to the data as well, and it's computationally much easier than either of the other two approaches. Finally, I'll revisit something that we did as a curve fitting example. As I pointed out in the curve fitting chapter, if I fit an n-1th polynomial to n data points, the polynomial will pass through all the data points. This counts as an interpolation approach, as well as a curve fitting approach. In the data set we're working with here, we have 9 data points, so I'll fit an 8th order polynomial to the data and plot it as a dashed magenta line. As before, we get a lot of big wiggles in the curve fit. Using a high order polynomial to interpolate data is generally a bad idea.